Now, here's the slope of a graph and a tangent line. We talked about that in the last problem, and so this is kind of how we get it by definition. So, given y equals f of x, the slope of the graph at the point a, f of a, is given by the limit of h approaching 0, and that's, again, our difference quotient, okay? And that's provided the limit exists. So in this case, the tangent line to the graph at the line through a, f of a, with the slope is given by this as well. So that's why when we did that before, the slope of the graph is the limit of the secant line, and that's also the tangent line. And so this is where we get that by definition, and we had to kind of come up with it before. Now, if the function f is continuous at a, then we have the limit as h goes to 0 of f of a plus h is equal to just f of a. Okay, and limit 3, which is this one up here, will be a 0 over 0 indeterminate form. We're evaluating the limit where we require algebraic simplification. Usually it means we're going to have to start canceling things out until we get down to the final thing. And so if you remember, like last time we ended up with like h plus 4, and before that we had h's on the bottom, h's on tops, and all that stuff. And so we had to simplify it as much as possible to actually get to that point. Now, the derivative, how do we get that? Well, for y equals f of x, we find or define the derivative of f at x, and it's denoted by this f prime of x. So that's what our derivative is going to look like. And the derivative is going to be as follows. F prime of x is equal to the limit as h approaches 0 of, guess what, a difference quotient again, f of x plus h minus f of x over h, if that limit exists. Now, if f prime exists for each x in the open interval a to b, then f is said to be differentiable over the interval a to b. Now, the process of finding this derivative is called differentiation. And we're going to do this, starting one way, and we'll get to a different way in a little bit. But the derivative of a function is obtained by differentiating the function. So, interpretations of the derivative. What do we do? Well, the derivative of a function f is a new function called f prime. Now, the domain of f prime is a subset of the domain of f. It's not the whole thing. It's just a subset. Now, the derivative has various applications and interpretations, including the following. The slope of the tangent line. So for each x in the domain of the derivative, f prime of x is the slope of the tangent line to the graph of f at the point x, f of x. Now, the instantaneous rate of change for each x in the domain f prime of x is the instantaneous rate of change, y equals f of x with respect to x. And then finally, the velocity. If f of x is the position of a moving object at time x, then velocity is equal to f prime of x is the velocity of the object at that time. Okay. So that's kind of some definitions, and we'll be looking at those here in a little bit. Now, how do we use all that to actually find the derivative? Well, to find the derivative, really what we're going to do is we're going to first find f of x plus h, and then we're going to find f of x plus h minus f of x, and then we're going to divide by h, and then we're going to do all the algebra to simplify it as much as possible, and then we're going to take the limit as h goes to 0. Now that's the key. If we do it in that order, it usually turns out pretty easy. The key step really though is eliminating everything that we can as much as possible in step 3. So when we do that derivative here in or the limit in step 4, then that's going to make it a lot easier problem. We just plug in a number and we get our value. Okay, so let's come back and we'll do some example problems with finding the derivative.